Let's solve a second diffuser problem, this one involving an ideal gas. Air enters a diffuser operating at steady state at 540 degrees R, 15 psi, and a velocity of 600 feet per second. It exits with a velocity of 60 feet per second. The ratio of the exit area to the inlet area is 8. Assuming the ideal gas model for the air and ignoring heat transfer, determine the temperature in degrees R and pressure in psi at the exit. Let's lay out our storyboard. We always begin with a schematic. We're dealing with a diffuser, and the air flowing through the diffuser is going to be our system. So the air molecules between the inlet and the outlet of the diffuser is our system, which I've shown with this boundary line. Now, a diffuser always has a smaller velocity at the exit than it does at the inlet, but it has a greater pressure at the exit than at the inlet. And so gas is compressed in diffusers. The given data is that T1 is 450 degrees R, P1 is 15 psi, and V1 is 600 feet per second. Now at state 2, the velocity is much less, at 60 feet per second. And we're told that the area at the exit is 8 times as large as the area at the inlet. So let's draw a TV diagram of this state. Air is a gas. There's no vapor dome on this TV diagram. State 1 is easy to plot. It's a temperature of 540 degrees R, and it's a pressure of 15 psi. So state 1 we'll plot here. Now where is state 2? Well, we don't know the temperature or pressure of state 2, but I do know that the pressure at state 2 will be greater than the pressure at state 1. So P2 I'm drawing here as a greater pressure than the 15 psi pressure. The only thing now that's unknown is whether or not the specific volume is less than state 1 or greater than state 1. But remember, gas is compressed in diffusers. So state 2 is going to have a specific volume that is less than the specific volume at state 1. So we'll plot state 2 over here. And again, we've got an unknown temperature and an unknown pressure. We'll model this as an open system operating at steady state. There's no mechanism for doing work, so the power output is 0. We're told that there's no heat transfer taking place between the system and its environment. We're going to assume that the potential energy change is 0, and we will treat air as an ideal gas. And we want to find the temperature and pressure at the exit of the diffuser. Let's begin with the continuity equation. We know that the mass flow rate is the area times the velocity divided by the specific volume. And we know that that is true at both the inlet and the exit. So these terms are equivalent. We also know for an ideal gas, specific volume is given by the gas constant times the temperature divided by the pressure. Let's substitute RT over P for specific volume in this mass flow rate ratio. So now we have area times velocity divided by RT all over P is constant. So that value is at state 1 is the same as it is for state 2. The R values cancel, and we're left with this, that area times velocity times pressure divided by temperature is constant. That is, it's the same at state 1 as it is at state 2. Well, we're asked to solve for pressure, so let's do that. The pressure at the exit is the pressure at the inlet times the ratio of areas, A1 over A2, times the ratio of velocities, 1 over 2, times the ratio of temperatures, this one 2 over 1, and recognize that A2 is 8 times A1. Now, we can't solve this expression yet because we don't have T2. Let's see if we can get that from an energy balance. Our energy balance is dE dt is 0 because we're operating at steady state. It's Q dot minus W dot plus M dot times change in enthalpy plus the change in kinetic energy plus the change in potential energy. Well, Q dot and W dot are 0, as is the change in potential energy. We're going to be looking for state 2 properties. So let's digress here momentarily and find the enthalpy at state 1. Well, we can do that with the air table at 540 degrees R. We can directly get a value out of the table for H1. Now, with that known, we can calculate the enthalpy for state 2. Let's rearrange what's left of our energy balance and solve it for H2. Well, let's see, it's simply equal to H1, which we just got out of the table, plus V1 squared minus V2 squared over 2. Now, here, you will recall that here we've got velocity squared, and so we have feet per second squared, which gives us units of feet squared per second squared. But we need energy units here, which will be basic English units of foot-pounds force. Well, how do we get from feet squared per second squared to foot-pounds force? We divide by G sub C. And if you don't recall what G sub C is, go back to the very first lesson on units in this series, and I will explain it there. So we have a G sub C is 32.174 foot-pounds mass per pounds force second squared. And that will convert feet squared per second squared to foot-pounds force per pound mass. Well, now we simply convert foot-pounds force to BTUs, and we get a value of H2 is 136.18 BTUs per pound mass. Let's find the temperature in the air table that's associated with this value of enthalpy. Well, 136.18 is between these two values in the table, which is to say that our temperature is between 560 and 580 degrees R. Now, I'm not going to do detailed interpolation here. I've done that in the past. At this point, you should be able to interpolate this value. I've laid out the expression. And I calculate that the temperature at the exit is 569.7 degrees R. So with T2 known, now we can solve our mass balance for the final pressure. It's the initial pressure, 15 psi, times the area ratio, and A1 will cancel, times the velocity ratio, 600 over 60 is 10. And then this is the exit temperature we just calculated, and we were given the initial temperature of 540. Calculate that the final pressure is 19.78 psia.